Hello, everyone. My name is Don. I'm an assistant professor from Penn State University. Today, I'm going to talk about a paper, Spatial Independent Range Sampling. This is a collaboration with Jeff Phillips, Michael Matheny, and Fei-Fei Li, when all of us were affiliated with University of Utah. With the wide adoption of mobile devices and IoT sensors, big spatial data has become ubiquitous. So these data may come from your favorite map app or ride-sharing app, IoT devices, or even social medias. So these data turns out to be very useful in a lot of applications ranging from traffic analysis, transportation optimization, to personalized site recommendations. One of the common scenarios in spatial data analysis is that a user is browsing and analyzing data in an interactive map environment. So as shown in a slide, so we may actually have a map show how electricity is generated in the US. To get a better understanding of the data, user may want to zoom in or zoom out to get a detailed or aggregated result. Besides, they may also want to move into an arbitrary range to compare it against with other areas. So in such an interactive application, we should be able to explore the whole space, in an interactive manner. So further, the underlying data may be too large to visualize. Hence, we may actually want to see some aggregated results or represent data points. Last but not least, based on the underlying data, user may also pick some randomized recommended data points based on weights assigned to them. So one of the ways to achieve all of these in an interactive manner is to build a system that provides exact results with very low latency. However, this is usually not practical as these systems are either still too slow to show results in split second, or they may consume too much computing resources. Fortunately, there is another promising approach. So in a lot of cases, people don't really need to get exact results to get an idea of their data and make decisions. In fact, they're pretty happy with approximation with guarantees. This opens up an opportunity to trade off between query performance and a results accuracy. So in past years, this particular approach has been growing into a thriving research areas called approximate query processing, or AQP in short. So with an AQP approach, a lot of approximate algorithms relies on random samples drawn from underlying data. So as we can see, there's a natural need to withdraw spatial samples on the fly in such an interactive spatial analysis platform supported using an AQP approach. So one very important thing we want to highlight here for withdrawing samples is independence. So in statistics, there are a lot of tools, including the central limit theorem, and most of the concentration bounds rely heavily on identically and independently distributed random variables, or we call it IID random variables. Having independent samples will bring convenience in analysis and also make continuation easier when we're not really happy with the current results. For example, we can have 1,000 sample withdrawal to calculate an unbiased estimator of some aggregation. If we think it's not accurate enough, we can draw another 1,000 sample to improve it without throwing the first 1,000 away. Further, not having independent samples can also be dangerous. So as shown in the figure in the slide, if the sampling method we leverage, in this case, is the green one, if it is not independent, so we may actually run into unfixable bias in the final results. So other than independence, we also want our sampling method to be able to explore arbitrary spatial ranges, have very low latency in withdrawing a small number of samples, and also have low cost in preparing, in pre-processing and storage. With all of these achieved, we can finally start building a practical interactive spatial analysis platform with an AQP approach. So in this paper, we call this particular problem the spatial independent range sampling problem, or in short, SRS problem. So formally, there are two different kinds of flavors of SRS problem, namely the uniform SRS problem and a weighted SIRS problem. So in a uniform SIRS problem, a query withdraws K samples uniformly from the data residing in a query region, and in the weighted version, each data points in a data set is actually associated with a positive weight. Thus, a weighted SRS query withdraws K random samples where each data point residing in a query region has a probability proportional to its share in the total weight of the region to be sampled. So even though there is no previous work studied particularly the SRS problem we study, we found that some paths can be extended in a straightforward way to do this. So the classic Okins method can withdraw samples from any tree-based index structure. So its basic idea is to traverse the tree randomly and report a valid sample if it reaches a point residing in the query region. Otherwise, it will just reject it. So it is very straightforward to apply this method to any traditional spatial indexes like R trees. However, this requires a lot of random number generation for each of the sample because there is a very high chance of rejection. Based on our analysis in the paper, the cost of RNG or random number generation is actually one of the major bottlenecks in these sampling algorithms. As a result, Okins method is slow and not practical in a lot of real-world applications. So there is another paper published in BLDB 2015 working on generating spatial samples on the fly. So the main idea is to optimize Okins method with a sampling buffer attached to each of the tree node. So with the help of these sampling buffers, we can avoid expensive random number generations when the request number of samples is small. However, this method does not provide any inter-query independence, generally speaking. It will provide exactly the same set of results when querying the same region 2 different times. So this violates a very important property we want from our samples, which is the independence. To actually fix this, we have to keep replenishing the sampling buffer, which makes it even slower than Okins method sometimes. So finally, the last baseline is pretty simple. We just get a full exact range result from a classic spatial index like R tree, and then retrieve the samples from the returned result set. This method is apparently not ideal because we have to make a full range search before we can retrieve any samples. To actually get a good performance, we propose a new sampling framework to solve these SRS problems. So we started from a simple observation that the uniform IRS problem, independent range sampling problem, on a single dimension sequence is actually trivial. So if we want samples between index range from S to T, we can simply generate a random number between them and report the corresponding data. So with that in mind, we can leverage different kind of space decomposition strategy, for example, space filling curves, KD trees, like quad trees to lay out our spatial data in a linear manner. So now when SRS query is issued, we can use exactly the same like decomposition strategy to decompose the query region into multiple continuous like index ranges on our linear data layout. So at this point, we pretty much reduce a SRS problem into a discrete weighted sampling problem plus a bunch of uniform IRS sampling problem on a single dimension. Specifically, for each sample we want to report for our SRS query, we first randomly pick one of the index range resulted from the decomposition of the query region. So each of the index range have a probability proportional to the number of its containing data points to be actually picked. Here, we can use Walker's ALIS method to solve the weighted sampling problem in a constant time. And now with a continuous range picked on our linear data layout, we just need to generate a random number in that range to get our final sample. To make it a concrete solution, we need to apply some space decomposition strategy into it. So a natural way to build our linear data layout is to leverage space filling curves. So in our paper, we take the z-value curve as an example. The z-value space filling curve will naturally decompose the space in a quad tree-like manner. So in this case, we can just lay out our data in a linear space cost, and the cost of each of SRS query is a combination of the space decomposition cost for the query region plus k constant number cost to withdraw the samples. Note that a space decomposition cost of a query region using the z-value linear quad tree decomposition strategy is actually related to the number of points covered by the region. Thus, the worst case query cost can be as bad as O n plus k, where n is the total number of data points. So in this example, we can see in the slides, now we can decompose the query region 2, 2 to 4, 5 into 6 different kind of ranges. So where 3 of them actually have some data points in it. So now, for each of the sample we want to report, we just need to pick a random range from the blue, yellow, and brown ones, and then pick one of the points randomly from the range you pick in a first stage to actually report. So another way that we can decompose our space is using KD trees. So generally speaking, KD tree in each level, we're decomposing, we're picking one dimension and partition our data into 2 parts equally. So in this case, we still have a space cost of O n, but we have a query cost which is still plus the k constant time of sampling, but the space decomposition cost is guaranteed to be square root n, which is a very good number without independent from the result size in the given range. So for a higher dimension, if we have a d-dimensional data using KD tree, we can achieve n to the 1 minus 1 over d plus k Curie cost in our framework. So with our example, we can see we have a Curie range here. So we have a KD tree on top of it, and we can see right now we have range 1, j, which is from 4 to 5, 7, 8, and 9. It's actually the results of decomposition of our Curie region. Then right now we just need to pick one of those 4, and then roll another random dice within the region that is as the outcome we pick it out to report as a final sample. As you notice, we actually have some general principles in building these kind of concrete solutions. So generally speaking, we can accommodate our data layout with any spatial index. So the principle of the reduction is pretty much each of the tree node we have in our spatial index is corresponding to a continuous interval on data storage. So if a node U is a descendant of V, the interval of U is also completely covered by node V. So once we have that, how do we actually build the data linearly? Data linear layout is simply do a DFS on the tree. So as soon as we hit a leaf node, we just concatenate it to the layout, concatenate to the end of the layout. So with this method, we can generalize we can generalize our framework to R trees, diagonal trees, or whatever spatial index that you want. But still, we have the KD tree as the best bounds for Curie regions as MBRs, which is guaranteed by the information theory. So now we know how to do this for uniform SRS problems. Now let's look at the weighted SRS problem. We can use the same reduction. So we still decompose our Curie region into a bunch of one-dimensional continuous ranges, but then our problem becomes weighted one-dimensional IRS problem. So theoretically, the best results is you can achieve this by O1 space cost and O1 sample cost, but it's very, very complex and never really implemented in practice. So it's not really practical at all. So the way we get around with it is we build a dyadic tree that can decompose a Curie range, like a 1D Curie range, into a set of intervals. And then we pick a random interval and traverse down a corresponding subtree to actually get our results, to actually get our weighted sample on a 1D region. So in this case, we call this method a dual tree method because we have 2 trees. One tree is the space decomposition tree to decompose our spatial region into continuous index range on the linear data layout. And we also have a dyadic tree that decompose each of the continuous Curie range into a set of intervals to facilitate our weighted 1D RS problem. To further optimize it, we actually observed that each of the index range generated by the space decomposition actually maps to a corresponding subtree inside the spatial index as well. So in this case, rather than having another tree to support a 1D RS problem, we just decompose everything into a bunch of subtrees, and then we pick one of the subtree and randomly traverse down there. So this is pretty much, you can see, you combine the dyadic tree and also the space decomposition tree into one tree. That's the reason why we call this method a combined tree solution. So note that there are different kind of methods. We talk about different kind of z-values or KD trees or even Oken's method. So different methods can actually have different better performance in different kind of scenarios. So for Oken's method, it's very good for non-selective Curies where the Curie has a selectivity greater than 10%, and you only ask for a very few numbers of samples, let's say less than 100. So our solution works for most of the cases, but needs a boost time. And also on boundary lead point where some of the points are actually outside of Curie range, we still have a very thin possibility of rejecting samples. So in this case, we can eliminate a rejection by just scanning through all the boundary leaf nodes and get rid of all the points which is not residing in the actual Curie region. So in this case, we propose a hybrid method. We start from like using the Oken method, start to like get some samples as soon as possible, while like we're doing like the space decompositioning on our thread to prepare to yield samples in our proposed solution. So once that is done, we can actually start. We can actually stop yielding samples from Oken's method and then start to do yielding samples from our method. And then we can spin out another thread to actually scan through the boundary nodes to completely get rid of the rejections. And when that is reached, like we can actually generate our sample at a very, very low cost at a very high throughput. We also discussed how to supporting updates. So we pretty much incorporate the idea of LSM tree. So it has a huge design space to explore, but generally speaking, we organize our data structure in multiple levels. In level 0 is just a range index, or you can just put whatever, you can just put raw like data set you can scan through it. And then asynchronously, like lower levels will be merged into higher levels, and each level other than level 0 is actually an SRS structure. So when like a particular SRS query comes, so it will like do the range query on level 0 and issue the same index ranges to all of the levels to do the SRS query. Then we can build a top level alias structure to pick like which level we want to withdraw each of the sample from. And then like inside each of the, once we know which level we want to sample, we can use exactly the same algorithm that we used in our previous slides to actually get a sample for the final results. Finally, let's look at some evaluation numbers. So our evaluation are conducted on a server with 250 gigabytes of RAM, and our like program is implemented in Rust 139 with the PCG64 MCG, our like random number generator. So we conduct we experiment our methods and all the baseline methods on 3 real-world data, which is the small one USA road network nodes, which have 24 million points. Twitter has like 40 million points, and OSM has 2.68 billion points. By default, we will withdraw 1,000 sample, and also like each of the region is square-like and roughly have 0.1% selectivity. And we also take 1,000 query, 1,000 query like for each of the runs and take the average as our final results. As you can see, our methods KDS and ZBS for weighted ZB tree combined and KD tree combined achieves the best results among all the methods. Specifically, it achieves 1 to 3 orders of magnitude better results, and we can see like some of the results from the baseline is not even better than the straightforward QTS. This is because when the selectivity is very low, having all the results may actually not be a bad idea. So we further look into what is actually happening while our method is faster than other people. We do the CPU breakdown, and we can see our methods KDS with and without rejection, KD tree combined with and without rejection, spend most of the time in effective RNGs and also doing alias construction. So this indicates that we don't really waste a lot of time in generating RNGs, eventually become a rejected sample. So you can see for Oken's method, they spend more than 80% or sometimes even more than 95% of their time in just doing wasted RNGs. We also do proof of concept of how to support updates using our LSM idea. So generally speaking, insertion is much faster with ZB trees because generally we can just do a sorted path merge to actually do the merging in different levels. And for the KD tree, you have to reconstruct the structure every single time. But acute latency KD tree is better because it has like better theory bounds and also immune to pathological cases. So in summary, we are talking about approximation approach to achieve interactive spatial data analysis. And we know that independent sampling is one of the foundation operations. So sampling framework, like we propose, is relying on multi-dimensional problem to the 1D reduction, and we explore different kind of space decomposition to make our solution solid. So we also extend our method into weighted SRS problem, and the key principles of our design is minimize the number of RNG calls and avoid rejections as much as possible. We also talk about a trade-offs between hybrid methods, between different methods, and propose a hybrid method to do this. And also we have an LSM tree-based idea solution to support updates. So in general, we achieve 1 to 3 orders of magnitude performance improvement of comparing with all the baselines. So thank you so much for your attention. If you have any questions, please let me know. Thank you so much.